Happy Monday, everyone. Hope you guys had a great weekend and are ready to start a great week this week. Just a review of this week's schedule. There's a slight change to what's going on Thursday. So today we're going to finish up separable differential equations that we kind of started that last week. That didn't show up on the exam, but we need to finish up that section. That's section 7.3. I'm sorry, 5.7. I've got different sections going on in my head at the same time. So 5.7, got the end of that. Not tomorrow, Wednesday, we're actually going to be going over one last section in chapter 5. That is section 5.10 on hyperbolic trigonometric functions. Now you might be wondering, what in the world are those? We'll get into that on Wednesday. But Thursday, I believe we have, let me check my schedule here. There is no quiz scheduled because we just came off of an exam. So don't worry about that. That's our last day before spring break. And I've done a little bit of rearranging in the schedule. I printed out a schedule and we'll distribute that. But I've taken chapter 7 and chapter 6 and actually switched them. And part of the reason that I've done that is after reviewing some of the material, you're going to get a lot more out of chapter 6 if we do that after chapter 7. Because there's some cool things that we can prove in chapter 6, but we need the techniques that are in chapter 7. So I've switched those two. And we're going to start into chapter 7 on Thursday, but the first section in chapter 7 is actually a review of integration techniques. So we're going to kind of summarize all of the techniques that we've had up until this point for if I hand you an integral, what approaches do you take? So that's what we're going to do on Thursday. So for today, let's just go ahead and jump in to finishing up section 5.7. So this is on separable differential equations. Okay. Now, one of the things to remind you of is again, a differential equation is an equation where the solution that we're looking for is actually a function, or in fact, a collection of functions. And just like the way that we solve an equation where the solution is a number, the way that we solve some of those equations differs depending on the type of equation that we have. Same thing is true for differential equations. Depending on the kind of differential equation we have, we're going to solve it in different ways. So we saw, if you have a separable differential equation, what that means is you can write it in the form some function of y times y prime equals some function of x. So you can manipulate the equation until you can get it in this form. And then the technique that we used, we wrote y prime using that Leibniz notation. Then we put the dx on the other side. And then we integrate both sides and then keep going, right? That is how we dealt with a separable differential equation. So the question immediately comes, what do we do if it's not separable? Well, one answer to that is if we can take something that's not separable and turn it into something that's separable, then we're good. We can solve that and then go backwards, okay? So it turns out that if you have a differential equation that's of the form y prime equals f of some function of both x and y, where f of x, y is what we're going to call homogeneous, and I need to define what that means, then you can turn this into a separable differential equation, okay? So the idea here, I'll give you a minute to write. So the idea here is that if we have an equation y prime equals some function of x and y, where this is not necessarily separable, okay, we can't stick the x's on this side and the y's on this side, but it has a different characteristic. It's homogeneous, and I'll explain what homogeneous means. Then you can actually take this and turn it into a separable differential equation. So first, there's two things that I've got to answer here. First, what in the world does homogeneous mean? And then once you know that you have this situation where this thing is homogeneous, how do you turn it into a separable differential equation? So let me answer the homogeneous question first. So let me give you a definition here. F of xy is homogeneous if you plug in tx and ty, wherever there's an x and a y, it turns out that's the same thing as t to the n times f of xy. Now, again, let you copy this down. F of xy is homogeneous if, when you plug in tx and ty, you end up being able to pull all of those t's out and you get t to the n times the original function. Now, before you freak out, let me give you a few examples here. And when I give you a couple of examples, this will make sense. So for example, let's look at the equation f of xy equals x squared y minus 4x cubed plus 3xy squared. Okay, what I want you to notice here, and this is actually kind of what we're tracking, is that the combined powers of x and y here are always 3. Okay, there's 2 x's and a y here, that's a total of 3 things. There's 3 things here, and there's 3 things here. That's actually what we're going to mean by homogeneous. So let's plug in tx and ty where there was an x and a y before. So instead of x, we're going to have tx, and instead of y, we're going to have ty. Okay, so everywhere, I'm just sticking in tx and ty for where there's an x and a y. Now what I want you to notice here is that there's actually 3 t's, so you get t cubed here, you get t cubed here, and you get t cubed here. So in other words, I can pull that t cubed out, and everything that's left is just the original function, x squared y minus 4x cubed plus 3x squared y. So in other words, I get t cubed times my original function. So this is actually a homogeneous function. So the idea of homogeneous is simply that you have, one conceptual idea of it is that you have the same number of things multiplied together throughout the function. Okay? This would be called a homogeneous function of degree 3 because we ended up with t cubed here. This one over here is called degree n. So it just depends on how many powers of t come out. Let me give you another example here, all right? We'll do a few examples and then this will make a little more sense. Let's take a couple other examples here. All right, let's try f of xy equals x squared minus 2xy. Can you see what's going to happen here? Let's plug in tx and ty wherever there's an x and a y. And I think you can see that what's going to happen here is we're going to get a t squared And here we're also going to get a t squared. And I can pull that t squared out, and what I end up with is the original function. So this is homogeneous. Homogeneous. And its degree, in this case, since I have a t squared in front, it's degree 2. All right? That kind of makes sense? All right, now it doesn't have to necessarily look like that. Let me give you another example. What if it was x times the natural log of x over y? You know, this one looks a lot weirder. If I have tx and ty, then let's do tx, natural log of tx over ty. And what you'll notice here is that the t's cancel there, and I'm left with t times the original function. So this is actually homogeneous. And what's the degree here? It's degree 1. Okay, now, lest you think that every function is homogeneous, let me give you one last example here. If I had x plus y squared, this one will not work. Can you see why? Okay, if this is x plus y squared, and I plug in tx and ty, I'm going to get a tx, but I'm going to get a t squared, y squared. Notice that I can't pull the t's completely out of the function, just leaving the function left over. That will not work here. So this is not homogeneous. That one is not homogeneous. So that would not be an example that would work for us. Okay, so the point here is that if we have an equation, we know how to do separable differential equations. If we have an equation that's of the form y prime equals one of these things that's homogeneous, then we can turn it into a separable differential equation. Okay, so let me give you, let's take a couple of examples here. We'll talk about how to turn it into a separable differential equation in a second. But so if I take the example, y prime equals y squared over x plus y. So first of all, I want you to notice this is not a separable differential equation. If I bring this over, there is no way to get the x on one side and the y on the other side. They're kind of intermixed. It's because I have this x plus y term here. So this is not separable here. However, you'll notice that this function right here, if I call that f of xy, so f of xy, if that's y squared over x plus y, then if I plug in tx and ty, I'm going to get a t squared on the top, and on the bottom, they're each going to have a factor of t. So canceling one t up here with these, then I've got a t out front, and I have my original function here. So this is homogeneous, so I can turn this into something that's separable. Now, I haven't shown you how to do that yet, but what we've concluded here is that we'll be able to do that. So I'll show you that in a second. Here's another example of one that's not separable, but that we would be able to do this with. So if I had y prime equals y squared over x squared plus xy, notice this function right here, erase this, it's not the same. If this was my f of xy, you'd get a t squared on the top and a t squared and a t squared here. So the t's would all cancel and you would actually have your original function. So this would be homogeneous. It would actually be homogeneous of degree 0. So this is not separable, but we can turn it into a separable differential equation. Okay, so how do we do that? That's kind of the big question. All right, so let's see if we can answer that. Okay, so if we have an equation of the form y prime equals f of xy, where this function right here is homogeneous, then what we do, the technique that we use to turn this into a separable differential equation, is we let y, basically we let y over x be a new function or a new variable that we're going to call v. So in other words, y equals v times x. And what we're going to do is we're going to substitute this into this equation. Now the equation is dy over dx equals this thing. So we need an expression for dy as well. Okay, dy, using the product rule, we have the first times the derivative of the second, v times dx, plus the second x times the derivative of the first dv. Right? What we're going to do is we're going to substitute that into this equation, and you're going to see something kind of magical happen where this equation ends up turning into a separable differential equation. Okay? So let's just take an example here. All right. Let's do y prime equals x plus y over 2x. Okay. Now, one thing to notice right away is that this equation right here is not separable. You actually can't separate it. Okay, if we were to try, let's go ahead and write it as dy over dx. Well, one thing you could do is you could write it as x over 2x plus y over 2x. Okay, so in other words, dy over dx is 1/2 plus y over 2x. Now, if you were to go over here and stick the dx on the other side, 1/2 plus y over 2x times dx, that's actually not going to work because this y is sitting here. There's no way to get that y over here without leaving a y on that side as well. So this is not separable. However, if we let y over x equal some other variable v, and so then again y is v times x, and dy is v dx plus x dv. That's just our product rule from over here. Then what we're going to get here, so dy is 1/2 plus y over 2x dx. So what I'm going to do here is for the dy, I'm going to substitute in v dx plus x dv. And over here, I'm going to have 1/2 plus that y over x becomes v. So v over 2. So now what we're going to do here, let's put this on the other side. So we're going to have x dv equals 1/2 dx plus 1/2 v dx minus v dx. So in other words, x dv is 1/2 dx, half of v dx minus a full v dx gives us minus half of v dx. So in other words, I'm actually kind of tired of these 2's, so let's multiply everything through by 2. I just don't like having fractions there. So notice I again have a dx here in both of these things, so I can pull that out and I'm left with 1 minus v. And so now let's put the v's over here. So I've got 2 over 1 minus v. I'm going to put the x's on this side. What I want you to notice before we go any further is that this equation right now is separable. This original one we were working with was not, but this one is, and this is one that we can actually work with. Okay, so what we're going to do is we're going to now come up here and we're going to integrate both sides. Okay. You cannot really see this part here. Let's, rather than doing that, let's bring it over here so you can see it. Now the right side's easy to integrate. The left side is going to be a little more challenging. We'll have to do a u substitution. So u equals 1 minus v. du is negative dv, so dv is negative du. So over on this side, we've got a 2, and we've got 1 over u, and the dv is negative du. Okay. And then the right side, if I wait to integrate, still looks like that. So what we've got is negative 2 natural log of absolute value u equals natural log of absolute value x plus some constant that I'm going to call c1. Again, this is separable. We're going to solve it the way that we normally solve separable differential equations. Okay. So let's now solve for, well, let's substitute back in for u. And then I don't substitute in for u, so let's try that again. So u is 1 minus v. So now I need to unpeel this so I can solve for v. So let's put the 2 over on this side, make it a negative 1/2. Okay, then we're going to take e to both sides. We've got e to this thing, which is really e to the negative 1/2 natural log of x, e to the c1. We're going to give that a new name, d, like we normally do. Now this can simplify, but only if this 1/2 is no longer between the e and the natural log. And the way that we do that is we bring that up to become a power the way that we did before. Do you remember that when you have natural log of x to the r is the same thing as r natural log x. So all that we're doing is we're taking that coefficient in front and pulling it up to become a power. The nice thing about that is that then the e and the natural log are together and these go away and we simply end up with x to the negative 1/2. Okay, I should have an absolute value there, which is really d over the square root of absolute value of x. All right. Now we're going to drop the absolute value like we normally do. And we're going to get a plus or minus d. And then if we switch these, and we can call that plus or minus d, we can call that a c, and we can switch these. So v ends up being 1 minus c over the square root of absolute value of x. All right? So that's our equation solved for v, but we did a substitution. V equals y over x. So to solve for y, I need to go back and plug that back in. So y over x is this equation. So y is going to be, I'm going to multiply through by x. That is my equation. Solve for y. Now that looks super ugly. Okay, and you might think, why in the world would we do this? But the point is that this equation that we had before, there was no possible way that we could actually solve it for y, because it wasn't separable. This at least turns it into a separable differential equation, and that then allows us to solve the equation. Does that make sense? Now on your homework, I'm going to do one more example. But on your homework, I've only given you one of these problems because it's fairly lengthy. Okay, you only get one of these kinds of problems, again, because it's kind of lengthy. So let's try one more example here. Okay, let's do, for example, y prime. Let's do x squared plus y squared over 2xy. Now I want you to notice, again, this thing on the top makes this not separable. That's not going to work. But it is homogeneous over here. So if I plugged in tx, wherever there's an x, I would get t squared here, a t squared here for the y, and then over 2, and I'd get t squared again, one from the x and one from the y. So those would cancel, and I would get the original equation that I had before. So this would be homogeneous, and the degree would be 0. Okay, there's no t to the n out front. So this will work, and what we're going to do is we're going to let y over x. Well, let's write it with dy and dx first here. So dy over dx is x squared plus y squared over 2xy. And let's cross multiply here. So 2xy dy is x squared plus y squared dx. And again, you can see I can put the x over here, but this thing is going to be messed up. I can't separate this. So what we're going to do is we're going to let y over x be this other function that we're calling v. So y equals vx, and our dy is v dx plus x dv. That's what we're going to plug in here. Right? So let's try that in here and see what happens. So we're going to get 2x, and then y is vx, and dy is v dx plus x dv. Okay, that's what we get on this left side. And on the right side, we get x squared plus y is vx. So we're going to square that. Okay, so let's multiply some stuff out and see what happens here. So we've got 2x squared v squared dx, so that's this first term here, plus 2, then I've got an x, and an x here is x cubed, and then I've got a v dv. Okay, so that's those first terms multiplied out. 2x squared v squared dx and 2x cubed v dv equals, let's go over here and see what happens. So we've got an x squared dx plus a v squared x squared dx. Let's put all the dx's on one side, so let's bring this over here. So we've got 2x cubed v dv equals x squared dx plus v squared x squared dx minus 2 v squared x squared dx. Okay, this term on the other side. So one of these minus 2 of them gives me just one, negative 1 of them. Okay, now the other thing that I notice here is that I can actually divide through by x squared. I've got x cubed on this side and x squared over here. So if I divide through by x squared, those are going to go away, and I'm going to have one of these x's left over. So what I've got here is 2xv dv equals dx minus v squared dx. So let's factor out the dx. And I've got 1 minus v squared times dx. Now let's put the x over on the left side. Sorry, the x over on the right side, so that's going to be 1 over x. And the 1 minus v squared over here, dv, and suddenly again I end up with a separable differential equation. That's the beauty of this. Now it looks ugly getting there, but we end up at least at a separable differential equation. So we get to the point where we can actually do this. So let's integrate now. Again, the right side is going to be easy to integrate. The left side, the way that we integrate this, how are we going to integrate that? What you should notice is the top looks mysteriously like the derivative of the bottom, so I'm going to let u equal the bottom, and du is going to be negative 2v dv, which is really close to the top. So what we're going to get is that negative 1 over u du is 1 over x dx, integral of 1 over x dx. So if we integrate, we're going to get negative natural log of u equals natural log absolute value of x plus c. Let's call that c1 because we're going to do some flipping around here. Let's move that negative over. Natural log of absolute value of u is negative natural log absolute value x minus c1. Let's take e to everything. So we've got the absolute value of u equals e to the negative natural log absolute value x minus c1, which we can switch into e to the c1. And again, we're going to give that a new name. We're going to call that d. Just like before, if I can get that negative out from between the e and the ln, then they'll cancel each other. And the way that I do that is bring that negative up to become a power. So that means this is e to the natural log of x to the minus 1 times d. So those cancel, and I get absolute value of x to the negative 1 times d is the absolute value of u. And so dropping all of the absolute values, I get u equals plus or minus d times x to the minus 1. I'm going to give that a new name. I'm going to call that c. And u is 1 minus v squared. So if we substitute that in, 1 minus v squared is c over x. Okay, we're almost there. So switching these, 1 minus c over x is v squared. And so, let's see where the best place to continue this is. V is plus or minus the square root of 1 minus c over x. So we solved for v. That's not quite what we need. What we need is to solve for y. So what I do now is just substitute back in v is y over x, and then multiply the x over. So y equals plus or minus x root 1 minus c over x. Okay. So again, it's ugly, but at least it lets us do something that we could never do before. We could not solve this differential equation before because it's not separable. But because this side is homogeneous, if we do this substitution, v equals y over x, and put that in, we end up with a separable differential equation that we can actually solve. All right? Again, there's only one homework problem on this just to let you try working with one of these. This is not going to be a major emphasis on a quiz or anything, but I want you to at least get an opportunity to play around with this a little bit. Okay? So you should have some time now for some homework, and Ms. Barabo is there to answer any questions you may have. Otherwise, I will see you on Wednesday. Have a great rest of the day.